All right, y'all. Let's get started with today's notes. Yeah. So last time we talked about finding limits at infinity, which are extremely connected to horizontal asymptotes. And today we're going to be looking at limits at a point. So in other words, instead of trying to figure out what the function is approaching as x goes to the left and to the right on the graph, we're going to be looking to see what is the graph or the value of the function approaching as x gets closer and closer to a single point. So we have a pretty traditional definition of a limit here. If a function becomes arbitrarily close to a number L, which is going to be the limit, as x approaches a constant c from either side, the limit of f of x as x approaches c is L. Okay. So what that basically means is that if you have a function that is approaching a certain value from both the left-hand side and the right-hand side, then that is the limit as x approaches whatever x value we're talking about. Now, we'll get a little bit more into that, but first I want to really clarify that the existence of a limit does not depend on the function being defined at that x value. This is a pretty key point here. And so I'm going to show you three different examples to sort of illustrate this. So let's graph y equals 2x plus 1. Okay, pretty straightforward linear function. It's got a y-intercept of 1. The slope is 2, so up 2 over 1. Should have a graph that more or less looks like this. All right. So now what I want to do is answer a couple questions here. First, what is f of 1? Now, you tell me, what does f of 1 equal here? 3. Yeah, good. F of 1 is 3. We can see that right here. Now, when I say what's the limit of the function as x approaches 1, what I have to do is look at the behavior of the graph on either side of that x value and kind of follow it as it moves along and see what are we getting closer and closer to. So as we approach that x value, x equals 1, from the left, imagine you're like a little insect or something crawling on this graph, and you're moving in this direction. What y value am I getting closer to? 3. Yeah. And as let's say I'm on the other side. Okay, if I'm coming from the right, I'm getting closer and closer, x equals 1. What y value am I approaching? 3. If those two numbers are the same, then that is the value of your limit, which in this case is 3. Right? Pretty straightforward. So now we have a different graph. Let's do something that's almost the same, but just a little different. This one's f of x equals 2x plus 1, where x is not 1. All right, so we'll plot that exact same curve, but what am I going to do at x equals 1? This function's only defined when x isn't 1. So what's happening when x is 1? There's a hole there. Yeah, exactly. So we've got a little hole here. Now, what we're calling a hole on the AP test, they have a way fancier name for that. It's called a removable discontinuity. Removable discontinuity. Okay, also known as a hole. I'll call it a hole for the most part. It's way easier to, I think, to conceptualize, but it is called a removable discontinuity. It's sort of the correct term for it. Okay, so f of 1. All right, well now what's f of 1 equal? Nothing, it's undefined, right? There's no value there, so it's undefined. But if I were to ask what's the limit as x approaches 1, I'm still going to act like I'm like those two insects crawling towards each other, okay? So if I'm just like crawling along this curve, moving towards x equals 1, what y value am I getting closer to? 3. I'm not going to get there, but I'm going to approach 3. I'm going to get closer and closer to 3. And that's going to be true on either side. So while the function is undefined at x equals 1, the limit as x approaches 1 is still 3. You see? So the value of the limit does not depend on what the value of the function is at that particular x value. It's not the same thing. It might be the same thing. And a good question that we'll answer in a few days here is like, well, when are those the same thing? What will guarantee that the value of the function is the value of the limit? You might think about that, but that's not always going to be the case. Let me show you one other example here that is really pretty similar to this. It's the same graph, except the function is defined at x equals 1 as 0. So we'll go ahead and plot this exact same graph. It's got this removable discontinuity, or this hole. It does something like this. But at x equals 1, the function is defined as 0. So what we have is this little point kind of disconnected from the rest of the graph. But now all the x values are defined, right? The domain would be all real numbers rather than everything except for 1. So what's f of 1? 0. Yeah, the function's defined as 0 when x is 1. But the limit as x approaches 1 is still going to be 3. So when you're talking about limits, we don't really care whether the function is defined there or not, whether there's actually a point that connects these two segments. We don't really care about that. We only care about what are we getting closer to. Any questions about that? Okay, great. Okay. Now, there are some cases where a limit does not exist. Okay. The one thing that has to be true in order for a limit to exist, and maybe we should write this out separately. Okay, I'm going to just write this out. For a limit to exist, the right and left-hand limits must be equal. Now, when I say left and right-hand limits, what I'm really talking about is approaching that x value from the left and from the right. So like for this graph, as I approach from the left, this is the left-hand limit, which is 3. The right-hand limit is approaching from the right. That's also 3. Since those things are the same, we have a limit, which is 3. If they're different, then there's no limit there. There is a way to notate the different left and right-hand limits. Okay, left-hand limit will be written like this. Let me zoom in here. I guess you have it on your paper so you can see. But the key thing here is this little minus sign that's sort of in the superscript, like where you would write an exponent. Okay, if you see a minus sign, that means you are approaching that c value from the left, from negative infinity. The right-hand limit will have a little plus sign there. So it's possible that you have a left-hand limit and a right-hand limit, but if you just say, what is the limit? These two things are not equal, then the limit doesn't exist. There's just no limit there. So yeah, this is one case where you might not have a limit. Let me show you an example. So it says, find the limit of f of x as x approaches 1 of this piecewise function. So piecewise function is just a function that's defined differently for different parts of the domain. It's 2x plus 1, which is that same graph we already graphed 3 times already, but only for when x is greater than or equal to 1. So it would have like a y-intercept of 1, go up 2 over 1, but we're going to start it when x is 1. So this is going to be this portion here. And then the other part of the graph says when x is less than 1, the function is defined as negative x minus 1. So that would have a y-intercept of negative 1, slope of -1. We're going to put an open circle here because it is just strictly less than. Let's try to get that as straight as possible here. Okay, so here's my graph. So if I try to find the limit of this, as x approaches 1, you're going to approach x equals 1 from both the left and the right. And notice here, as I approach 1 from the left, just kind of following it along, what am I getting closer and closer to? -2. So the left-hand limit, and the way you would write that is like this. The limit as x approaches 1 from the left of f of x is -2. All right. I like the color there. That looks a little better. Oh, that's really hard to see up there. That's fine. As we approach x equals 1 from the right, what is the value of the function approaching? 3. So we would say that the limit as x approaches 1 from the right. Oh, you know what? I did not stay consistent with my color coding here, did I? You know what? I'm not. That's confusing. Let's change that. The limit as x approaches 1 from the right is 3. Now, a lot of times, like sometimes on a free response question on the AP test, they'll ask you, if the limit doesn't exist, explain why. And so what you would have to do is make a statement. It doesn't have to be like a paragraph or anything. You would say the left-hand limit and the right-hand limit are not equal. So if you want to say something, so the way you would say this is like find the limit. Okay, so the limit as x approaches 1 the limit as x approaches 1 of f of x does not exist. Okay, kind of like saying it's undefined. So we'd say it does not exist because the left and the right-hand limits are not equal. Now you don't have to write a whole sentence there. You could just say because the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. That little statement, that phrase, is what the graders are going to be looking for. They say, explain why there's no limit. Any questions? Yeah, great. Let's move right along here. Okay. Here's something else that could happen. Something that's called unbounded behavior. This is a case where the function is not approaching a certain value. In order for a limit to exist, the function must be approaching a specific number, not go off to infinity or negative infinity. So you want to be careful with these limits at a point versus like a limit at infinity of saying, oh, it equals infinity or it equals negative infinity, because it might not be the same on either side. In some cases, it is, like 1 over x squared. If I do, I think it does something like this. We might double check in Desmos. I think it does something like this. All right, so you can see that as x approaches 0 from the left and the right, the value of the function is just going to infinity. It's not approaching a specific value. Now, if on both sides we're going to infinity, we can just say it's infinity. And what we mean is it doesn't exist because of that divergent behavior, that unbounded behavior. So it's okay to say, oh, it doesn't exist. This does not exist. Does not exist Yeah, well, we know all these don't exist, right? But it's also okay to say infinity here because it's going to the same direction on either side. So doesn't exist. Now it's okay to say equals infinity. That's pretty widely accepted notation. But what it means is the limit doesn't exist because it's going to infinity. The limit as x approaches infinity for 2x. Okay, so this is a limit at infinity. This is what we did last time, right? So y equals 2x is just going to look like it's a regular old linear function with the y-intercept of 0 and a slope of 2. And as x goes to infinity, we can see that the graph is just going up forever. It's not bounded. There's no boundary. So that would also be infinity here.
Does it also not work because you can't go from the right side?
So the limit at infinity is going to work is defined a little bit differently than a limit at a point. So a limit at a point, you have to go from both sides. A limit at infinity is going to be defined as the value that the function approaches as x goes to infinity. Okay. So there's a slight difference in the definition there. Does that make sense?
Yeah, that makes sense.
You're right, because otherwise all the limits at infinity would all do not exist, right?
Yeah, because
you can't approach it from the right. Yeah. Good question. Yeah. Now, this is going to be something that doesn't happen too often, but you'll see it a lot of times with sinusoidal functions or other periodic functions, this oscillating behavior. Now, if I say, what's the limit as x approaches infinity of sine x? Let me just write, so the limit as x approaches infinity of sine x, this graph is going to do something like this, right? So this is what I mean by oscillating behavior, where it's not settling on any number, but it's also not going to infinity or negative infinity. It's just sort of bouncing between two different values, or maybe even multiple different values. But the point is that it doesn't actually settle on anything. So we've kind of talked about that a little bit in the last lesson, but here we've got a limit at a point. And so finding oscillating behavior at a point only happens on kind of weird functions. So here we have got sine of 1 over x squared. But you may not know what that looks like, and I don't think I can really do it justice by sketching it. So let me show you in Desmos what this would look like. Oh, can I pull up Desmos here? Oops, I'm just going to do one of these. There we go. Okay, so what was it? Sine of 1 over x squared, I think. All right. So the question is, what is this approaching as x gets closer and closer to 0? So it's not really clear, right? Like, what? Too much pixelation there. So maybe we should zoom in a little bit. You might get a better idea of what's happening here. Actually, can I zoom horizontally only? Is that possible? Oh yeah, there we go. All right. So what you're going to see here is that I could zoom in as much as I want. I'm not really going to get any more clarity. It's not going to really let me zoom in horizontally anymore. I'm not going to get any more clarity here. I could zoom in like as much as I want. Or you know what? Maybe I could just click this instead of trying to do it with my fingers. I'll just zoom in like this. Yeah, it's just like, what is even happening here? So what's happening here is we've got like a sine function, right? That's where the periodicity is increasing. Meaning like the distance between these peaks is getting less and less and less. And there are actually, this is kind of hard to envision, but there are infinitely many of these ups and downs. And the closer you get to the origin, the faster it's bouncing up and down. And so you really cannot tell what's happening at 0. Because the closer you get to 0, all you see is just more oscillations. So it's sort of weird. So anyway, this is not going to happen too often to you, but I do want you to see an example of like where you can have this kind of crazy oscillating behavior. I guess if you wanted to sketch the graph, let's go back to here. like I said, it's really hard to sketch out here. I guess I'd do something like this. Just like some ugly mess like this. Yeah. What is happening in there? I'm not going to throw too many of these at you, but I just want you to be aware that this is one type of function where you have a limit at a point that does not exist. So this is something that could cause the limit to not exist. This is oscillating behavior. All right, so that's pretty much it for today. Let's do some practice together before I give you the homework, okay? So let's see if you guys are really following along here. We've got this, this just kind of wild piecewise function, and I want to know what's the limit as x approaches -4. What do you think? So as we approach -4 from the left, and we approach -4 from the right, what's the value of the function approaching? 3. So that's the value of the limit. As long as both the left and the right-hand sides agree, you have a handshake, then that's what it is. What about the limit as x approaches 1? 1, good. What about as x approaches 5? 5. So these are 3 limits at a point that have a value, and it just is the value of the function. Okay, so now let's look at where x is approaching 2. So first, what's the value of the limit from the right? What's the right-hand limit as x approaches 2? Like if I approach 2 from the right, and I know it looks kind of weird because I'm drawing an arrow that's pointing to the left, but you're approaching it from the right. So what value is that function approaching from the right? 3. What value is the function approaching from the left? 2. So what's the value of the overall limit? There is none. It does not exist. Right? And that's because the left and the right-hand limits are not the same. All right, we got 2 graphs here. So I think I'll give you, we're doing pretty good on time. We'll give you like 5 minutes or so until I just kind of notice you're done. Let's see if you can do these 10 problems. See if you can find these 10 limits. All right, I know not everyone's done, but a good chunk of y'all are, so I don't want to keep you sitting and waiting here. Let's see what you got. Even if you're not done, that's okay. I think we can piece together the rest of these. So the limit as x approaches -3 from the right. What do we get for that one? -3 from the right. Oh. Yeah, it does not exist. What is it getting closer to? Yeah, -infinity. So you could put like does not exist, -infinity. Now it's going to -infinity. And the left-hand side is going to positive infinity, right? So if it was just asking, the limit as x approaches -3 just doesn't exist, period. Because it's not even going the same direction on either side. Okay, what about number 2 here? The limit as x approaches 2. Limit as x approaches 2. So this is for f of x. And let's see here. If we're approaching, I'm sorry, did I say -2? I meant +2. Yes. So as we approach 2 from the left and 2 from the right, what value are we getting closer to? -3. Yeah. You look at the next one. Yeah. Okay. Yeah. So yeah, well, what about -2 then? Yeah, it does not exist. Right. The left and the right-hand limits do not agree on that one. All right, what's g of 2? So this is just simply evaluating the function. No limit question here. It's undefined, right? There's no value here. So we would say it's just undefined. The limit as x approaches -infinity for g of x. Well, if this thing continues to go downward, then what will we say the limit as x approaches negative infinity is? Negative infinity. Yeah, it just keeps going down. All right. The limit as x approaches infinity for f of x. So what is the value of the function approaching? 0. It's approaching that horizontal asymptote. Yep. You see it's going like this way. That little dotted line is indicating the asymptote. Yes, sir.
On 5, can you not put does not exist because it's going to infinity?
That's what it means. Yeah, when you say infinity or negative infinity, it's really shorthand for saying it does not exist because it's going to negative or positive infinity. Okay. So that's why it's okay to say it's. I think it's kind of bad notation personally, but it's widely accepted notation.
Okay.
So
can you put does not exist for that? Or?
Yeah.
Oh,
yep.
Okay.
But you might find like if there's like a multiple choice question on the AP test, they might force you to pick between infinity versus negative infinity for those unbounded limits. Yeah. But sometimes not. So it's just good to know, like when you're writing infinity, what you're actually saying by that. All right, what's f of 4? Just evaluating the function. So yeah, when x is 4 up here, this point, yeah, there's nothing up here, but it is defined down here. So f of 4 is negative 1. The limit for f of x as x approaches 5. Does not exist, right? Due to unbounded behavior. So you can say does not exist. Let's go into infinity. Number 9. The limit as x approaches 3. 2, yeah. Yep. Just left and right hand limits agree. And then we've got the limit as x approaches, this is for f of x, this green one up here, as x approaches negative 2 from the left. Negative 4, yeah, good. So as we approach negative 2 from the left, the value of the function is approaching negative 4. Okay. So the last thing here is, we spend a lot more time on graphs and tables because I think tables, like looking at tabular data is a lot easier. And so basically, it's the same kinds of questions here. We're looking at the left and the right-hand limits. We want to know if they agree. So we've got a table of values here. And we want to know, as x gets closer and closer to 2, what's happening to the function. So let's just kind of break down the table first, and then we can answer the questions. So as we approach x equals 2 from the left, so this is the limit as x approaches 2 from the left, what is the value of the function approaching? Let's look at these values. 3.67, 3.76, 3.91, 3.98. What does it appear as though it's getting closer to? Yeah, 4. Yeah. Now, you see, yeah, so some of y'all said 6, and that's probably because you looked at, at x equals 2, it equals 6, right? So this right here is basically saying f of 2 is 6. But you got to remember that the value of the function is not necessarily the same as the value of the limit. When you're finding a limit, you're not really looking at the point itself. You're looking at the points around it. What is the value of the function approaching rather than what is the value of the function? Okay, so as we approach 2 from the right, so the limit as x approaches 2 from the right, from the left we are approaching 4. What does it appear as though we are approaching from the right? Yeah, it looks like probably 5, right? Because you can see these values are decreasing and kind of getting closer to 5. Now with the table of values, we really can't say for sure because it's very limited information. And so we are kind of making a prediction here. We're making some assumptions, definitely. But later on, when we have some more information, after we talk about continuity, we'll be able to say for sure what the limit is. Okay, so from the right, it's going to be 5. So what is the value of the limit as a whole as x approaches 2? Does not exist. And why does it not exist? Because the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. That little phrase is what the AP grader is going to be looking for. Now, why doesn't the limit exist? Because the left and the right-hand limits don't agree. All right, last one. Doing really good. Okay, good. So the limit as x approaches 0. So what is it as we're approaching it from the right? Yeah, we're getting closer and closer to 0. Right? The limit as x approaches 0 from the right looks like it's getting closer to 0. And what about the limit as x approaches 0 from the left? Yeah, also 0. Although we do see that when x is 0, the value of the function is 5. Now, like, how can that happen, right? Like, what's happening in this graph is really you have a removable discontinuity there. You have something like this going on, where like just at that one particular point is just defined elsewhere. So what's the limit as x approaches 0 then? 0. Yep. As long as these two things are the same, then you have a limit. Yeah.